Hello everybody, this is a video for Math 13-14. Today we're going to be looking at how to graph polynomial functions. If we look at this particular problem, I subdivided this problem into several sections, so that it'll be easier for all of you to follow me. As I go through each and every section, I will link each and every section to a particular rule or a particular theorem. So please pay close attention to what I'm doing, as well as what kind of theorem or what kind of rule I'm using. Let's read carefully this problem. For the following function, part A, we're going to use the leading coefficient test to determine the graphs in behavior. For part B, we will find the x-intercepts. We will state what happens at each of those intercepts, whether the graph crosses the x-axis or touches the x-axis and turns back around at each and every intercept. Part C, we will find the y-intercept. And part D, we will graph the polynomial function. When we graph the polynomial function, we will utilize the calculator, the graphing calculator. So make sure you have one with you. Part A. Use the leading coefficient test to determine the graphs in behavior. And the function that we will be using for this particular problem is f of x equals x to the fourth minus 4x squared. Now, in order for us to determine the graphs in behavior, what is a graphs in behavior? A graphs in behavior is really what happens to the graph at the ends. Okay? Remember, we're dealing with polynomial function. One particular solution that we might have, or the result, is when both ends happen to point up, like in this type of a function. Remember, this happens to be our quadratic function. Or we might have a scenario where we have a function that looks like this, f of x equals x cubed, where one side happens to point up, but the other side happens to point down. So for our function, what does it do? Do both ends point up? Do they point down? Does one end point up, point down? What happens? To determine, we have to use leading coefficient test. Again, this is the test that will show you the in behavior of the graph. Please remember, when you memorize these theorems, these rules, these tests, remember the name, because the name will tell you what exactly you're going to do. Since this is a leading coefficient test, we're going to be utilizing a leading coefficient. Okay? Leading coefficient test involves two parts. It involves the leading coefficient of the function, and we always represent that with a sub n, and the highest power of the function, which is n. We have four possibilities. And for the four possibilities, I'm going to create a little rectangle with 4 cells, where we will look at the highest exponent, n, that n being either even or odd, and we're going to look at for the leading coefficient, whether the leading coefficient is positive, greater than 0, or the leading coefficient negative, less than 0. Hence, we'll have 4 cells, 4 possibilities. Okay? The quickest and easiest way to remember this particular test is to look at the two functions that I gave you, the quadratic function and the cubic function, and remember the transformations. Let's look at the quadratic function. Notice how the highest power of this function is 2. Well, 2 happens to be an even number. So here, n is even. Look at the leading coefficient. The leading coefficient of the quadratic function is the number in front of x being squared. In our case, it's 1. Well, 1, it happens to be greater than 0. So here, n is even, and the leading coefficient is positive. We are in this first cell. N is even, and a sub n is greater than 0. Look at the ends of this quadratic function. Both ends point up. So right end points up and left end points up. But what happens during transformations? What if my leading coefficient happens to be negative? So now let's look at the g of x. G of x is negative x squared. Well, isn't that a reflection over the x-axis? In this case, our function g opening down. Isn't that what we know about quadratic functions? Well, look at this leading coefficient test. Now, our leading coefficient is negative, but the highest exponent is still even. So now we are in this cell in the box. Look what happens to the function. Both ends point down. Let's look at the case where n is odd. let's look at the second function, the cubic function. Do you see how the highest power is 3? 3 is odd. But in this case, the leading coefficient, remember the leading coefficient is a number in front of the variable to the highest exponent. It's 1. Leading coefficient is positive. The highest exponent is odd. We are in this box. N is odd, and the leading coefficient is positive. Look what happens to the ends. Right end points up. Left end points down. Now let's remember our transformations. What would happen if now I will multiply this x cubed by -1? Isn't that a reflection over the x-axis? So now the graph looks like this. Look what happens to the ends. Now right end points down and left end points up. We can utilize the idea of the leading coefficient test onto our function. Our function has a highest power of 4. And the leading coefficient, a number in front of x to the 4th, is 1. A sub n is positive, which is greater than 0. N is even, which happens to be in this box, where the right end points up and the left end points up as well. Okay? That was step number 1, or part A in this problem. Let's look at part B. Find the x-intercepts. And of course, we have to state what happens at each of the x-intercepts. Let's take our function, f of x equals x to the 4th minus 4x squared. Right? Remember, when we're finding x-intercepts, we will always let our function equal to 0. So let's take our function, x to the 4th minus 4x squared. Let's set it equal to 0. In order for us to solve this equation, we have to factor. Notice how we can factor a greatest common factor. Here, the greatest common factor is x squared. Once I factor out x squared, out of x to the 4th, x squared stays. And if I factor out x squared out of -4x squared, -4 stays. Okay, but we are not finished. Look what we have inside the parentheses. X squared minus 4. That's a difference of 2 perfect squares. Let's factor this into x plus 2, x minus 2, and please don't forget about the factor of x squared. Okay. Once our function is fully factored, and once we created an equation, remember we set our function equal to 0, let's take each and every one of these factors and set them equal to 0 to find our x-intercepts. When we take x squared equal to 0, remember this can be written as x times x. Take each and you will realize that x equals 0. Solve x plus 2 equals 0 for x. Subtract 2 from both sides. X is a -2. Take x minus 2, set it equal to 0. Solve for x by adding 2 to both sides. We found that we have 3 roots, or 3 places where the function crosses the x-axis. At x equals 0, at x equals -2, and at x equals 2. Okay, but please be careful, we have not answered fully part B. Part B says not only to find the x-intercepts, but we have to state the multiplicity. Okay. If the multiplicity is even, the graph touches the x-axis, but it doesn't cross the x-axis. It will touch and turn. If we have odd root of multiplicity, the graph will touch the x-axis and cross the x-axis at that particular root. Let's look at x equals 0. To know what type of multiplicity we have, we will go back and look at the factored form of the function and look at the exponent of each and every factor. Look at the exponent on x right here. X is being squared. Our multiplicity is 2. Number 2 is an even number. So we have even root of multiplicity. The graph will touch and turn. At x equals -2, let's look at the exponent on that factor. The exponent, the power is 1. Multiplicity is 1. Number 1 is an odd number. This is an odd root of multiplicity. The graph will touch the x-axis and cross at that root. Now let's look at x equals 2. X equals 2 came from the factor x minus 2. Let's look at the power. The power here, that little exponent, is 1. Multiplicity is 1. Number 1 is an odd number. We have odd root of multiplicity. The graph will touch and cross at that root. Okay, so now we have completely finished part B. All right, let's continue and look at part C. Now notice in part B we found x-intercepts. But our functions, they don't necessarily have to only cross the x-axis. They could cross the y-axis. So when the function crosses the y-axis, we call that area a y-intercept. So let's look at part C. How do we find the y-intercepts of the function, if there's any? All right. To find the y-intercept, we always set x equals to 0. So really what we're looking for is f of 0. Let's try. Remember our function, f of x equals x to the 4th minus 4x squared. When we let x equals 0, that means we're substituting 0 for each and every x in the function. Hence, f of 0 equals 0 to the 4th minus 4 times 0 squared. When we simplify, please notice that you get 0. So the y-intercept is 0, 0. It's the origin. It becomes the x-intercept, which we found in part B, and then it becomes the y-intercept as well, because it's the origin. Okay, now let's look at part D. How do we put it all together? To put it all together, we're going to take our calculators, and then we're going to graph the function. And I'm going to show you on the calculator how to do just that. To graph a function, we'll go to y equals screen. Let's type in our function. Remember, our function is x to the 4th minus 4x squared. Okay. Sometimes you might need to change the window depending on who used your calculator before. So if you don't see exactly on the screen what I see, then you might need to end up either zooming by clicking on zoom and using option number 2 or 3, zoom in or out, or clicking on the window and changing your x min, x max, x scale. So if you want to make sure that you see exactly on the screen to what I'm doing, make sure that your window looks just like this. Now, if I click on graph, here's my function. It looks like a little W. But what's important is for you to see a few things from this function and to make sure that you can link all the parts that we did to this particular function. Now remember, for part A, we used the leading coefficient test to determine what happens at the ends. And indeed, both of our ends are pointing up. That's exactly what we wanted. Let's look at part D. Part B. Part B says find the x-intercepts. Well, it's very easy to see our x-intercepts are at 2, 0, and -2. Remember going back to the window. Look at my x scale. My x scale is 1. That means that I have the distance between each and every hash mark on the x-axis is 1. So the distance here is 1 and here is 1. So I can count by ones. 1 and 2. Not only that, I can also go back to the table. Okay. Remember, to find the x-intercepts, we'll let y equals 0. Notice when y is 0, x is 0. That's one of your x-intercepts. Now, when y is 0 here, you have another one at 2. Now, if I go up to the negative axis, notice when y is 0, x is -2. So hence, here are my 3 zeros. -2, 0, 0, 0, and 2, 0. That's exactly what we found in part B. Now for part C, finding the y-intercept, of course, in this problem, 0, 0 is the origin, so it's both the x-intercept as well as the y-intercept. Now, going back to the graph one more time, let's look at the multiplicity. Look at x equals -2. The multiplicity of -2 was odd. The graph went down to -2, touched at -2, and then crossed at -2. Remember that the multiplicity on 0, 0 was 2? That was even multiplicity. Look how the graph went up to 0, 0, touched 0, 0, but never actually crossed the x-axis. It went back down where it came from. Look at x equals 2. You see how it crossed? It went up to 2, touched at 2, and actually crossed the x-axis by going up. That's touch and cross action. So indeed exactly what we found in part B.